Okay, if everyone can go ahead and open up your iPads, get up the class notes that we were working on yesterday, and try to follow along. So in class yesterday we were discussing experiments, where I discussed the cookie experiment, where we all discussed what a perfect cookie would have to taste like, and we worked on the independent variable of the cooking time to then change what our problem was. So we said that the cookie was too hard, right? Why is the cookie too hard would be our problem. The hypothesis was we cooked it for too long, so therefore we needed to develop our independent variable of the cook time and manipulate that to be able to come to a better conclusion as to what a perfect hardness would be on a cookie. Let's remember that with our control group, we decided that the control group needed to be the pans, the temperature that we cooked at, and the recipe that we used, as well as the amount of cookie that we placed down each time. So our independent variable we manipulated, the controls are all the other factors that will remain the same. And then finally we have our dependent variable. This was a measurable quantity that we would have as a result of the independent variable. And this was the actual hardness. Once we were done, how hard was the cookie? Okay? So that's a quick review of yesterday, and let's continue forward. Data collection must be unbiased. In order to get a clear depiction, a scientist must be able to go in and strictly look at the experiment, see what happened, and report on it. So common is the funding aspect of research. Nowadays, people will fund an experiment to prove that their product is safe for the market. However, if it is biased, it means that the scientist may have said, oh, you know what, I'm not going to report all the findings, or I'm going to skew the findings. So, no one died by using this product. However, a couple people might have been hospitalized or gotten very sick, right? They may not report the very sick. They'll just say, sure, this is safe for people to use. Sure, no problem. Go ahead. Bring it to market. All right, and then finally we have our conclusion. This is what our results are that we're going to spread out there for peer review. Remember that peer review is when we develop other people taking our experiment, repeating it, and now we have more and more data. Now we need all this data because our goal with a hypothesis is to expand our knowledge, and eventually maybe we seek to reach the point of being a theory. So let's go ahead and advance. Okay, now here we discussed in some classes knee pain while running, right? This would be our problem. So go ahead and take a second and think about how you could use scientific inquiry to diagnose knee pain, right? So the first question you ask is, okay, so why do I have knee pain? Then you come up with some hypothesis. Maybe it's time to get a new pair of running shoes. Maybe it's the surface that you're running on. Maybe you just don't have very good technique and you need a running coach. You could take any one of those particular features and then run your experiment. But remember, you have to isolate one. One has to be your independent variable, whether you change the running shoes or you change the way that you run or the surface that you run on. You can only test one at a time. Okay? So, now we come to the point of having a hypothesis. A tentative explanation for an observation or a phenomenon. Basically an educated guess. You've looked at the data, and now you're thinking, okay, I think this, or I think that, right? So in the running example, I went out for a run, and I said, oh, wow, I have knee pain. I wonder why I have knee pain. You know what, maybe I need to go and get a new pair of shoes. So I go to the store, I get a new pair of shoes, go out for a run a couple days later, I don't have any knee pain. Okay, must have been the shoes. But other times we know that our hypothesis might be wrong and we need to go back and try again. So it's an educated guess. You look at the information and then you try to say, okay, this is what I think it could be. Now, with that peer review, we have other people go through and run our experiment, and Of course, talking about cookies or knee pain is small scale, but when we look at the large scale, like later this year we'll talk about things like plate tectonics, we get into the realm of theories. This is when you have a generally accepted truth based on a large body of evidence. Large body of evidence, like so important that I'm just going to go ahead and underline that. You need a large body of evidence in order to hit the point of theory. Now, there's a key point to remember. Not everyone has to agree. Okay, there are plenty of people out there that don't believe in the Big Bang Theory. There's a slew of people out there that don't believe in the theory of evolution, right? Charles Darwin, by the way, the church does support this. But there are plenty of people that don't believe in it. So not everyone has to agree in order to be a theory. Okay, there might be some skepticism. And every now and then you'll hear about a theory that's been overturned. Now I'm not talking like check the papers each week, but there have been a couple in the last few years. Okay. Lastly, we have a law. And laws are really, really cool because there is no exception. Go ahead and underline it. No exception. See, I'll read it for you, right? Generalized statement about how the world behaves under certain conditions for which no exceptions have been found. So, my favorite example is if I were to take the entire class, right? We all go up, we climb upstairs, and then one by one I chuck you off the roof. I guarantee, because of the law of gravity, you're all going to move toward the ground. Right? Now, obviously, bad idea. Don't actually ever try that. But you guys all get the point, right? If we start chucking things, they're all going to move toward the ground. Now, in the case of students, like you're not all going to hit the ground because you start to pile up, but you get the idea, right? So let's not go and do that. The laws of motion, right? Newton's laws of motion apply in space exploration, right? Once we go ahead and push some of those probes, some of those satellites out into space, once they get their moving force, then they just keep going. You don't have to worry about, okay, wait, all right, let's run out there by Mars. We got to keep that guy going. No, it just keeps moving. It is really, really cool. So laws have no exception. All right, I'm going to pause there. Good, I wanted to go ahead and change the slide up. So the next thing that we want to talk about is developing a scientific model. Now, a model is anything that is going to represent a phenomenon, a process, or even just another item. For example, some of you maybe growing up, you had a toy model of a car, right? It's a model. It's not the real thing, but it looks like it. You can oftentimes make references to the real thing based on the model, right? Now that toy model, and this picture shows the globe from the World's Fairground over in Queens. Those of you that drive along the LIE, you might notice it off on the side. That's a representation of the Earth, right? So it looks like it, but it's not the real thing, right? Obviously, I mean, we'd fall through there. That'd be a problem. All right, so that's a physical model. Or maybe you have a model of an airplane, right? If you guys go up to Brother Gary's room, there are airplanes all over the ceiling. And you guys probably don't know who that is, but go upstairs, look in some of the classrooms. You'll see one with lots of airplanes, right? Those are all physical models. You can touch them, right? They are hands-on, okay? But other times we get into conceptual models. Okay, this is where we're going to go into phenomenon. This is where we're going to blend our knowledge, right? What we're gaining with things that we might think. It gets into the theoretical side of things. So we're going to talk later on in the next few chapters about space. We're going to get into the ideas of dark matter and antimatter. These are things that are conceptually discussed, right? These are conceptual models where it has to exist because we know X and we know Y, but we can't actually see it. We can't actually, touch it. We can't. So it's conceptual, all right? The other one that we like to talk about is the mathematical model. And a mathematical model is great because it's something that applies today. When you guys hear about climate change and they're saying, oh, well, the CO2 concentration or back in the earlier part of the Industrial Revolution, we had this, you can actually make a graph you can use an equation to be able to show what you're talking about. So that's a mathematical model, right? Graphs, equations, hello math class, right? But other times, you'll have something like plotting the course of a hurricane, which you see on the left. Now that's something that you guys are going to start paying attention to because we're still in hurricane season. We still have to worry. Think back of when Hurricane Sandy hit, right? So we're still in hurricane season, and if you guys check the news over the next few weeks, you're going to certainly see hurricane paths. You're going to see storm tracks. And that's simply going along and plotting the data to be able to make a prediction, right? And that's really where all these models are going. We want to be able to make predictions. We want to be able to make certain statements based on what we've seen, based on the patterns that we've analyzed. So this comes back to what's the goal of science, right? And if you guys look back in your notes, we said to understand the natural world, right? To take our acquired knowledge and make predictions about the natural world. How do we think this is going to go? Because otherwise, what are we doing, right? Why bother studying where there's going to be an earthquake if we can't predict when one might happen? And we'll work on that. All right, so I don't want to get too far ahead, but hopefully you guys are seeing the pattern. Hopefully you guys are working through this. And don't be afraid after this video to go ahead and ask some questions. Now, with models, we get into an idea of a system. Okay? Now remember, physical models, everybody reach out, grab your arm. Right? Maybe touch your head. Right? You are part of a system. Right? Your entire human body is a system, and it can be broken down into simpler parts. And we'll get into some of the details on that, but let's just look at the two basic types of systems. For earth science, we want to know where's the energy going, and we want to know, is there an exchange of matter? So we have our two types. We have a closed system, and we have an open system. Now, I want you guys to stop and think of a sun tea jar. If you don't know what that is, go jump in a lake. But a sun tea jar would be like a big mason jar where there's a silver lid on top usually, and during the summer you pour some water in there, you put some tea bags in, screw the cap on, you just stick it out in the sun. Now you do that in the morning, you come by in the afternoon, and you hold on to the water, or onto the jug, and you feel that the water has gotten warm. And you look inside and the tea bags have actually activated, right? Just like when you pour a cup of tea with hot water, only you allowed the sun to heat it up. But you look inside, you still have the same amount of water. So what's happened is you've had an exchange of energy, but you've had no exchange of matter. You still have the same amount of matter inside, the same amount of water. We call that a closed system, right? If we were to do it the other way, where we took the lid off the top, well, on a really hot day, you might come back and maybe there's half the water's gone. At that point, think, the lid's off, it's an open system, right? We've had not only an exchange of energy, but that energy, the water heated up, and then what do we know about water? It evaporates. So now we've had an exchange of matter. We've lost matter. But let's think about a couple other ones. How about the human body? Are you guys an open system or a closed system? Go ahead and think about it. Think to yourself, ask, do I exchange energy? Right? Do you guys put off heat? Anybody? Anybody put off heat? Do any of you sweat? Right? Maybe some of you are actually athletes, right? You certainly can feel when your body's putting off heat, right? You can feel the sweat pouring out. I mean, we were certainly feeling it last week. So we definitely know that we exchange energy, but do we exchange matter? That's the question. Well, if you think about eating breakfast and then what's going to happen later in the day, you guys probably realize that, yes, in fact, we not only exchange energy, but we also exchange matter. So we are an open system. An automobile, you put the gas in, it puts exhaust out, it's an open system. But the point here is, let's talk about earth science, right? What is the earth? What is the earth? Is the earth an open system, where we're exchanging energy and matter all day, or are we more of a closed system? Well, when we get into it, think about gravity holding everything down to the Earth. And pretty much all the gases, all the water vapor that goes up, all the objects that go up, come back down, right? So we are generally a closed system. There are two exceptions. Every now and then we get a meteor shower, so that's a slight, and when you think about the scope of the size of the Earth, a very, very slight increase in matter. And we do lose some hydrogen and helium out into space. So that's another small exception. But Earth, generally closed system. All right, I'm going to stop there. And at this point, I would like you guys to go ahead and open up in your Google Drive folder the vocab that I posted. And I want you to compare the vocab that you have with the vocab that I gave you. And make sure that you study. I'm going to turn it over to Brother Tim.